Nucleic acid quantity and quality may be determined by electrophoresis and spectrophotometry. Electrophoresis results on a stained gel shows 1, no or very low quantities of nucleic acid if a band is absent. 2, contaminating nucleic acids if there are bands of unexpected size. 3, nucleic acid fragmentation if smears rather than distinct bands are present. Additionally, for RNA, the upper ribosomal band, 28S in eukaryotic cells and 23S in bacterial cells, should be about twice the intensity of the lower band, 18S in eukaryotic cells and 16S in bacterial cells, to show good integrity. Spectrophotometry can determine the concentration as well as presence of contaminants and is based on the absorption of light by chemicals. Concentration is directly proportional to the absorbance, and based on Beer's law, concentration is equal to absorbance divided by epsilon times B, where epsilon is the extinction coefficient or molar absorptivity, a constant for a particular substance which measures how strongly the substance absorbs a wavelength of light. B is the length of the light path. Nucleic acids absorb mainly at a wavelength of 260 nanometers, so absorbance at 260 nanometers is used to determine concentration as well as purity. The extinction coefficient for a particular sequence of nucleic acid is based on extinction coefficients at 260 nanometers for all bases in that sequence. However, generally, nucleic acid concentration is calculated based on the average extinction coefficient values of DNA and RNA. Using the average extinction coefficient values at 260 nanometers, path length of 1 centimeter, and absorbance at 260 nanometers of 1, double-stranded DNA has a concentration of 50 microgram per ml, and single-stranded RNA has a concentration of 40 microgram per ml. And thus, nucleic acid concentration in microgram per ml corrected for turbidity by subtracting the absorbance at 320 nanometers is calculated using the equation nucleic acid concentration in microgram per ml is equal to absorbance at 260 nanometers minus absorbance at 320 nanometers multiplied by the concentration of the nucleic acid when absorbance is 1 at 260 nanometers multiplied by the dilution factor. Dilution is necessary to ensure the sample absorbance measured at 260 nanometers is within the range of 0.1 to 1, within which there is a linear relationship between concentration and absorbance. The dilution factor is the total volume of solution per aliquot volume. So if we take 10 microliters of a DNA solution, add 90 microliters of water to dilute it, the total volume is now 100 microliters of DNA solution. And the dilution factor is 100 divided by the initial aliquot volume of 10. That is, the dilution factor is 10. Additionally, for accurate absorbance readings, the DNA should be in a slightly alkaline buffer. Example, 10 millimolar tris HCl, pH 7.5, to maintain DNA structure. The spectrophotometer zeroed with the same buffer to correct for any background absorbance, and a cuvette used suitable for absorbance readings in the ultraviolet range, say a quartz cuvette, so the cuvette itself does not contribute to absorbance. Purity measures used are the absorbance at 260 nanometers divided by absorbance at 280 nanometers and absorbance at 260 nanometers divided by absorbance at 230 nanometers. The first, absorbance at 260 nanometers divided by absorbance at 280 nanometers, is around 1.8 for good quality DNA and 2 for pure RNA. Lower values suggest contamination with, say, protein. The second, absorbance at 260 nanometers divided by absorbance at 230 nanometers should be around 2. Lower values suggest contamination with salts. If there is contamination, accurate quantitation of the amount of nucleic acid will not be possible. In summary, 1. Among the methods used to evaluate nucleic acid quantity and quality are gel electrophoresis and spectrophotometry. 2. Gel electrophoresis can indicate success or failure in extracting nucleic acid, whether the nucleic acid has sufficient integrity, and if there is contamination with nucleic acids of unexpected size. 3. Spectrophotometry can determine nucleic acid concentration using the equation nucleic acid concentration in microgram per ml is equal to absorbance at 260 nanometers minus absorbance at 320 nanometers multiplied by the dilution factor multiplied by the concentration of the nucleic acid when absorbance at 260 nanometers is 1. For spectrophotometry, to determine purity, uses the ratio of absorbance at 260 nanometers divided by absorbance at 280 nanometers, which should be around 1.8 for highly pure DNA and 2 for pure RNA. To show low salt contamination, the absorbance at 260 nanometers divided by absorbance at 230 nanometers is used, which should be around 2. Now let's review the topic on how nucleic acid quality and quantity can be tested with some questions. Question 1. Which of the following are important factors when considering the suitability of isolated DNA as an analyte for a given technique? 1. Amount or concentration of DNA. 2. Purity of the DNA. 3. Integrity of the DNA. A. 1 and 2 only. B. 2 and 3 only. C. 1 and 3 only. D. All of them. The answer is all of them are important. Question 2. Does lane 1 on the gel show A. Good quality genomic DNA, B. DNA of poor integrity, C. RNA, D. Impossible to say. The answer is genomic DNA of good quality, as the molecular weight is very high in the expected range for genomic DNA, and there is no smearing showing low integrity. Question 3. When a 0.1 ml aliquot of a specimen is added to 9.9 ml of diluent, what is the dilution factor? The answer is, based on the equation, dilution factor is the total volume divided by the initial aliquot volume. Total volume, Vt, is equal to aliquot volume plus diluent volume, that is 0.1 plus 9.9 milliliter. Dilution factor, Vt divided by Vi, is equal to 10 divided by 0.1, which is equal to 100. Question 4. In a cuvette with a 1 centimeter path length, a solution of double-stranded DNA diluted 10 times gives a reading of 0.457 at 260 nanometers and 0.246 at 280 nanometers. Assuming that a 50 microgram per ml DNA solution gives an absorbance of 1 at 260 nanometers, what is the DNA concentration in the sample? Is this DNA pure? To answer this question, first let's assume absorbance at 320 is equal to 0 and there is no turbidity. Then based on the equation, nucleic acid concentration in microgram per ml is equal to absorbance at 260 nanometers minus absorbance at 320 nanometers multiplied by the dilution factor multiplied by the concentration of the nucleic acid when absorbance at 260 nanometers is 1. Nucleic acid concentration is equal to 0.457 times 50 times 10, which is equal to 220.85 microgram per ml. Purity is indicated by the ratio absorbance at 260 nanometers divided by absorbance at 280 nanometers, which is equal to 0.457 divided by 0.246, which is equal to 1.86. That is, the DNA is pure. If you found this video useful, you may also be interested in videos on DNA extraction, which can be found on this channel. Please do also give the video a thumbs up and subscribe to support the channel. Thank you.